Yeah, so we ended the last lecture by defining what the 6 subcategories and seeing all the 6 subcategories in the bounded graph category of A2. Yeah. So maybe just as a reminder, non-empty subcategory of K, which is our triangulated category throughout. Right, when I write K, it's an essentially small triangulated category. And this thing is thick if it is closed under suspension and desuspension 2 out of 3. If we have 2 guys in a triangle in there, the third is as well, and it's also closed under sums. And so maybe we have seen this example of dbKA2, so maybe let's look at another example that has somehow quite a different flavor and ties in what we had at the very start of our first lecture about the motivation. So we saw this result there that if we start with a commutative ring, then certain nice subset of the spectrum of the ring actually give us the 6 subcategories. Yeah. So let's look at that in an example, and maybe what's the nicest one we can think of is, first let's say we have an algebraically closed field, just to make things a little bit easier, and then we take R to be the polynomial ring in one variable. So let's investigate. We know somehow spec of R should come into play here. So how does it come into play? Good. So what are the finitely generated modules over Kx? Well, certainly we have Kx itself, the polynomial ring, and then we also have quotients of the polynomial ring by some powers of a maximal ideal. Right, something like that, where alpha where alpha is just some element in K. Yeah. Good. So how does that all vibe together? David has drawn us this beautiful picture, which you later learned are Ausländer Reitenquivers. We can draw an Ausländer Reitenquiver here as well. It's not quite as, it doesn't contain all this nice information that we had when we were working with thinking quivers, but it still has a lot of good information in there. So we could think of perhaps over here. Perhaps I could be so stingy with space and just go over here. We certainly have the polynomial ring, and then we have, for each of our alphas, we have this simple that we get by quotienting out, this maximal ideal, and then we could, by multiplying with x minus alpha, get to the module where we quotient out the square of x minus alpha, and then we can go back by just taking the quotient, and we can do that, keep doing that, right? And we get a picture like this, which we call a tube, and we get a bunch of tubes which are labeled by closed points of the affine line. Okay, we're algebraically closed.
What's the meaning of the arrows going up?
Multiplying by x minus alpha. Yeah. So these are our, what the meanings are, these are our irreducible maps. These are kind of these minimal maps maybe David was talking about. Good. And then, I mean, this is not, well, maybe this is fine, right? K, the polynomial ring, of course, maps into all of these, but we don't see the maps in the picture because where would we start, right? We map arbitrarily high into this.
Can you also say what, like different algebras, they don't have that. Like,
Yeah, oh, that's a very good point. The tubes don't see each other.
and you don't have, why do you have no combined x minus alpha, x minus beta?
They're not indecomposable.
They're not
Guys.
indecomposable. They're not indecomposable.
Yeah. These are all the ones that Sorry?
Yeah, I was just not used to thinking.
Okay, good.
Thanks.
All right, so that's the picture we get. Okay, so what should we? So what happens? Well, if we think of 6 subcategories, we always have. Maybe we can just call that K. K is the boundary category. And then we always have K, and we could somehow link K as just being the whole spectrum of R. Okay, so what else do we have in the spectrum of R? So what is the spectrum of R, right? This is just all the x minus alphas, the maximum ideals here, and 0. Right? 0 ideal. So that's spec of R. And somehow we see already this is not so bad because each of those points, each of those close points in spec of R actually gives us one of these tubes. Yeah. And what more can we think? Well, the as Natalie just remarked very very importantly, the tubes don't see each other, right? So you're not going to be able to build, like if you have something in that tube and something in another tube, you're not going to be able to build something new that doesn't already lie in these tubes. So somehow they're independent, but on the other hand, if you have just one guy in this tube, you can build all the other guys by iterated cones and extensions and etc. Right? So if you just have one guy in your tube showing up in your 6 subcategory, the whole tube shows up, but nothing more. You're not going to exit the tube. Yeah. So each of those close points here is going to give you a 6 subcategory over here. So somehow the picture, then you could think of the whole 6 subcategory as belonging to spec R. You could think of the empty subset belonging to the trivial 6 subcategory, which is just 0, and then you could think of each, maybe it's just like this, and you could think of each of your closed points as your tube that has x minus, that it has this module at the bottom. Okay. But of course, so it's not quite as simple as saying, okay, the points in here correspond, or the closed points in here correspond to 6 subcategories, because of course I could take any combination of tubes. I can just pick and choose my tubes, and this is going to give me a 6 subcategory. So what it looks like is that the lattice of 6 subcategories of K are just unions of closed points, or if you want, unions of closed subsets. Unions of points and the whole thing. So we can just say unions of closed subsets of spec.
Don't I get arbitrary subsets?
Yes, because I can really choose an arbitrary subset of the tubes, and it's going to give me a 6 subcategory. I can pick whatever tubes I want.
Yeah, but why did you emphasize unions of closed? If I just get the power set.
No.
No.
They're close.
I'm not going to get.
Okay.
I'm not going to get the power set.
Closed
I'm not going to
subsets
get.
are finite subsets of.
Yeah,
Exactly.
Without the inertia.
Sure.
you'll not get the generic point.
You're not going to get the generic point. And I mean, like, why do I write it like that? I could just say, oh, the power set, but not stuff that contains the generic point. Okay, which would maybe be more complicated to write that. But the thing is, this is very close to the general state. Yeah?
Could you remind me what TK is? Is the lattice associated to?
Yeah, of course. So that's a good point, and that's very important. Right, T of K is, so far, just the set. Maybe I haven't told you that even. So this is a really good point of thick subcategories of K. Thank you very much. This is going to be throughout. So for now, just the set of it.
Lattice of this, okay.
Yeah, but we don't know that yet, right?
You said thick subcategory.
Sorry?
You said thick. You mean lattice of?
Well, I'm saying set because I haven't shown you it's a lattice yet. Okay. No, it is the lattice of thick subcategories. Yes.
You didn't write set, you wrote something else.
Thick of thick.
Oh. What have I done? Okay. Yeah, okay, I'm sorry. I understand the confusion. That's very weird. Okay. Okay, good. So what do you have as our general result? So this is the theorem that has shown up in the motivation without any details. So this was this result of Hopkins and Neumann, which was settled there from the Syrian rings, and then Thomason stated it for arbitrary commutative rings. So if R is commutative, then because I changed my order, so what do we have? T of perf R is actually, and okay, now I say as a set, so we have to stick with that. And now is the Thomason subset of spec of R. So it's controlled by spec of R. And what it corresponds to are these Thomason subsets. What are these? Pretty much what we had up here. They're union of closed subsets, but only of closed subset with quasi-compact complement. So these are unions of closed subsets with quasi-compact complements, I guess. Yeah. Good. So we have that. So that's the general setting. And maybe to make this result a little bit more powerful, because I mean, yeah, that these things have the same cardinality. Okay. Probably often happens quite a lot, right? But what about what is the deeper meaning of this? And this is the crucial. This is the crucial observation of the whole lecture series, which is that T of K forms a lattice under inclusion. And remember, as we have up there on the board, K is an essentially small triangulated category, but any essentially small triangulated category, and T of K is the set of the subcategories of it.
Can you just, this is the closed subsets need the quasi-compact complement, not the
Yes.
right?
Yes, exactly. So you look at closed subsets with quasi-compact complements, and then you take arbitrary unions of those.
Sorry, is this now an observation from the theorem, or is this now a new observation about T of K in general?
This is a new observation about T of K in general. So no K in the theorem. This is an observation that we're going to use to strengthen our theorem.
Does that also mean it's a complete lattice? Because you closed up on the source.
Yes. Yeah. I show you why in a moment. I'll show you why, or maybe not why, but I'll show you a nice way to see this in a moment. TFK forms a lattice under inclusion. Why is that? So let's start with this, right? If we have, what do I call them? If I have, of course, a complete lattice, even here, complete. If I have a subset of 6 subcategories, we know we had this really good observation from the audience in the first lecture. If we have arbitrary meets, we're going to have arbitrary joins. And what is the meet of a collection of 6 subcategories? Yeah, Sam is showing it. It's just the intersection. Yeah, because what is a 6 subcategory? It's just a thing that's closed under a bunch of stuff. So the intersection is still closed under the same things. So that's fine, but of course, maybe mostly for notational purposes, we also have a join. And the join is the 6 subcategory generated by the union of the guys, and that's how I'm going to write it with these analogue brackets. Which just means generate as a 6 subcategory. And this is just a small, we know what that is, right? This is the smallest 6 subcategory that contains all of the 6 subcategories in T. Okay, so this was our observation just about any set of 6 subcategories of essentially small triangulated category, and now we can say that this is actually a lattice isomorphism, where we look at this as a lattice under inclusion. Right. So.
It's covariant.
Sorry?
It's covariant. The orders are the same or reversed.
No, this is really under inclusion here. So you look at the inclusion of the Thomason subsets. Yeah. Not reversed inclusion. Okay, maybe before I tell you this thing, let's then take this ahead, because we had this good question. Is this a complete lattice? Well, yes, it is, because this is a complete lattice. Okay. I don't. Maybe let's talk about this later. But the point is, like, we already see now that the lattice of the subcategories in this case, where R is commutative, is somehow controlled by a space. Yeah. So it's somehow continuous in that sense. But we're going to make this a bit more precise in a moment. First, what I want to do is, I told you that 6 subcategories are really very natural subobjects to work with, right? And we have this extra condition which is closed under summons, and you might be like, why do I want to close under summons, right? Why not just triangulated subcategories? And this ties back in with the motivation we had at the start, which is that if you study localizations, you can be studying fixes. So, say something about localizations. And we have the crucial observation here is that if we have a functor between essentially small, between triangulated categories, so we have triangulated categories, then a triangulated factor from K1 to K2 is just a functor which is additive, and everything else you would want from it. So it's an additive functor. And what do you want from it? Right, it should preserve the triangulated structure, so it should commute with suspension, and it should send triangles to triangles. So I'm going to use sigma just for all my suspensions in all my triangulated categories. I don't think this will cause any confusion, but if it does, then let me know. So composing sigma with F should be naturally isomorphic to composing F with sigma. And then we have that, if we have a sense triangles. Okay, and the lemma we can maybe just prove in our head, which is that the kernel, which are just all the guys in K1 that get sent to 0, viewed as a full subcategory of K1. This thing is a full subcategory. It's probably not so hard to convince ourselves that this is true, right? Because if you have if an object A gets sent to 0, then so does its suspension because it commutes to suspension. If you have a triangle A, B, and C, and two of those get sent to 0, then you get a triangle over there with 2 zeros on it. So the third one is also a 0. And also it's closed under summons because it's a commutative. Right? So good, that's a fixed subcategory. So kernels of exact functions are fixed subcategories. And that's the crucial point. Right? If we have a localization, then its kernel is going to be fixed. So maybe we can do an example. Take the product of paper. And one thing you could do, you could say, okay, you want to localize this. Think of this either as a co-localization or just localizing this as a category, whatever is most comfortable. And you could just say you want to invert alpha. Yeah? Invert alpha gives us a localization. And what does this do? You go from Q and you invert alpha, so 1 and 2 become identified, and you have one guy beta, one non-isomorphism beta between them. Well, what beta becomes, right? So this goes actually to the loop, where gamma is that you can think of going along alpha inverse and then along beta. So you get this localization. And this localization gives you a localization on the perfect derived category from, so let's call this L, from D perf to Kronecker to D perf of the loop. And what's the loop? It's just a polynomial. The path algebra of the loop is just a polynomial, which we already know what it is. All right. So, what does this localization do? Well, it just inverts the map. It inverts the map from P1 to P2 given by alpha. Yeah. So, in other words, when you evaluate this map, this is an isomorphism. That's just the same thing as saying that the cone of the L of the cone of alpha is 0. Maybe the nice cute thing, if you haven't really ever thought about this before, what's the cone of this map? literally that thing as a two-term complex. If you haven't seen it and tried to prove it, it's a little bit of like what's an undergraduate string, right? You don't have to do anything. You have to remove the curve. Yeah. Good. So we have that. And what is like the cone? If the cone of alpha vanishes, because we know that our localization is an exact function, it's a triangulated factor, so it's going to preserve triangles and suspensions. So that means that the whole thing subcategory generated by that thing is going to be mapped to 0. In fact, this is everything that gets mapped to 0. The kernel of L is the Sig subcategory generated by the kernel of. Now let's draw our usual picture. As you see, that's what we're all about here. So what does the non-derived category of chronicle look like, roughly? So you have some component like this, which are just like your projectors maybe live here. Yeah. And then you have a bunch of pre-projective here and suspensions of pre-injectives. But the important part is that our guys here lie here. Then you have a bunch of tubes, right, like we had over here, where, well, these tubes are labeled by closed points. Of the projected line. And at the mouth of one of these tubes sits magically the cone of alpha. And then you get another one of those components, just the shift. And then you get tubes again. Okay, so what happens if you invert this map between this map alpha from P1 to P2? Well, what you're going to do is you're going to kill that cone. That cone is going to die. All the other tubes stay unaffected. They just live happily because they don't map in any degree to this guy. What happens to your pre-injected and pre-projected components? Well, P1 and P2 should get identified, and actually what happens is that because you get kind of maps that land, you also get maps from here to here that land in that cone, the whole thing becomes compressed to a single point. So that's like K lambda. So over here you have this guy becomes compressed to K lambda, the suspension of it. And what are your tubes labeled with? Well, you still have as many tubes as before, but really morally you removed one, right? So these are closed points of the affine line. And what is that? Exactly what it should be, namely the perfect derived category of the polynomial ring, which we have over here. Right? Good. So kernels of exact functors are 6 subcategories. And that's this illustrated. This example illustrates, but also a fact is that every single subcategory.
Can I ask you to understand this picture now? So you're saying that if you look at pre-image, you have the open inclusion of P1 to P1?
If I look at the, sorry.
If you look at the pre-image map under L, you have the open inclusion P1 to P1.
Yeah, exactly. I mean, what guy did we remove here? Maybe the origin. It depends a bit on your labeling of the tubes or whatever. But you remove the origin.
Thanks.
Could you repeat what the P1 and P2?
Oh, they were the projectives. Yeah. they are the projectives of Kronecker. So P1 is the simple projective, so if I work with right modules, which I do, this is a guy that's going to look like, right, this is just pure representations. This is a guy that looks like that, P1. And then P2 is a guy that looks like that. And I include K in the first or in the last. You're not included. And then when you take the cone of that map, right, this is injected, you're just going to get the co-kernel, so you get a guy with K here and K here, where your alpha map becomes 0 and beta is an isomorphism. And that's what sits at the bottom. Any other questions? All right, so the fact is also that every Sig subcategory can be realized as a kernel of a triangle function. And what you're going to do is you're going to take the Vernier function so if you have every Sig subcategory T, so if you have, we write that as K mod T, and you get that by formally inverting all the maps whose cone land in T. Right, so that's telling us that Sig subcategories are precisely kernels of a factorial. Good, so we should be thinking of them when we think of localizations. Good, I think I'll go an example in the other direction, but you can reverse that example if you want, yeah. So I want to talk about something that has come up quite a lot in your questions, and that's going to be the next portion of the lecture series, and that's distributivity. So perhaps we should start with a definition of what distributive means. A lattice L, well, no, I want to keep that. I want to start going in another direction. So it's where we eventually get to. So those who know, and that's where we're leading. The first thing I want to do is I want to revisit this theorem. And what we said is that somehow this perf of R is controlled by a space. And okay, naively I can just say, okay, it's controlled by spec R because it's somehow determined by this topological space spec R. But actually, what I would really want when I say something is controlled by a space, I want to say it is actually the lattice of opens of a topological space. So the question is that the lattice of opens of a topological space? And Sam is giving me a thumbs up. It is. Yeah, because if you have a spectral space, so something that looks like spec of a commutative ring, then we can form its so-called Hoxter dual, due to Hoxter. And that is the topological space, so we call that X, what's the word?
V.
XV?
Check.
X check, yes. I like that better. We call this X check. And it has, this is the topological space with a underlying set X, so it's still the same set. And okay, well, what are the opens there? Thomasson subsets. You can show Thomasson subsets. You can show relatively easily that this is still going to give you a topology, right? I mean, we defined it as a union of those subsets. So we believe that. Now, the beautiful thing is, I mean, the deep thing here is that if you start with a spectral space, spec of R, this is still going to be spec of S for some reason. It's still going to be a spectral space. But relevant for us right now is that this means that T of perf of R is on the nose controlled by some topological space, namely commutative of spec of R.
Different analysis. Oh, sorry.
No, okay, thank you, buddy. I almost made that mistake, but I saved myself. But you're absolutely right. I mean, it is actually controlled by a spectrum.
And is the construction like this, or does it come from, like, can you construct the ring which it corresponds to through R, or?
I don't know. I mean, like, so we can
You
noise.
cannot construct R from the spectrum, so
No, yeah.
No.
So the way the proof works is that you can encode, probably not because maybe time reasons, but you can encode what it means to be spectral, just in topological properties. And the proof, the way that the proof works or works through is just taking that.
Proving
that. So
okay.
I'm not sure.
So there's no construction in the ring.
I don't think, I'm not sure.
So there's another way of defining a spectral space than just purely in terms of lattices.
Yeah.
And in this case,
So my question is does it live to rings?
Oh,
The construction.
okay. So maybe not actually, right? Because maybe you can find some. Maybe not. Sorry, what were you going to say?
so you can also define a spectral space in terms of lattices. This might be a little later actually. And in this case, like taking the hospital just corresponds to taking the opposite lattice.
Yeah, that's true.
Flip everything over.
Okay.
But even then, you don't really see what the see what the ring
for
is.
rings, it's not.
it's not controlled. You can't get a control description of a ring for a spectral space. It's an existence statement. There's no lift.
It's just an existence statement, but I mean, I'm not aware if you can ever construct a ring. I mean, my guess is no, but I don't know.
Yeah.
Not the way the proof works. It's a good question. Okay, good. So this is good, and especially right. We have seen what happens when we plug in the polynomial ring. We actually quickly computed that example. So not much bad things should happen if we still stick with the polynomial ring and we just tweak it slightly, right? Okay, so we have kx, which was our little loop. And all we're going to do is we're going to put a grading on this thing, very innocent. So we put a z grading with x in degree 1. And what happens now is like we get a bunch more we get a bunch more kind of graded shifts of every module, but we get fewer maps between them, right? Because the maps now have to respect the grading. So we get something that looks like a double infinity curve. Kind of the quiver picture, if you're happy with quiver pictures, as some of you are reputedly. Good. So not a big change, you think, but no, it is. We can show precisely what the lattice of the subcategories is of the graded polynomial ring, of the category of the graded polynomial ring. And somehow, I don't know that yet, but like what this is, we have seen non-crossing partitions before, and now they show up again. These are precisely the non-crossing partitions, the lattice of non-crossing partitions of Z together with a point at minus infinity under the natural linear order. particular, maybe we're not gonna talk about the idea because I want to make a little bit of headway. In particular, T of dv per kx is not O of x for any topological space. So here you are not going to be able, see it better. You're not going to be able to find a topological space X that controls this lattice, not even with any trickery or what you want. And what's the reason for this? The reason is in the title of our section. The reason is that this is not distributive.
Show that explicitly the Hofstadter dual does not correspond really to R, because you consider the spectrum of Z, like Hofstadter dual it's a duality, but Z is the initial object ring. You're going to set that to.
Yeah. So we cannot reconstruct.
Oh, that's very easy.
Okay.
You can choose a ring, but it has nothing to do with the integers.
So if it's functorial, then the initial object.
No, I mean, like, I see the question. Right? I mean, you can you find some ring, right? Could you find some ring that you... That's the question, right? But,
You can,
maybe not so
and it
easy.
has nothing to do with the original ring.
I know, yeah. Yeah. But like, okay, let's keep this debate for a minute. So, what are we doing? Distributivity. Definition. A lattice is distributive if whenever we have objects A, B, and C, and I'm going to call my lattice L, in L, then meets, well, the thing is meets distribute over joins. So if we take the meet of A with the join of B and C, then we can pull in the meet. So this is the meet of A and B, join the meet of A and C. So that's the definition. Fun exercise is that being distributive is self-dual. So if you switch joins and meets here, it's still true. So a lattice is distributive if and only if joins distribute over meets. Binary joins distribute over binary meets. This is like if and only if any true such thing. We have A join B meets C. Is A join B meets A join C. All right. So example. And that's the crucial point for us here, is that if X is a topological space, then O of X is distributive. Okay. So how do we see that? If we have three opens, well, we know that meets and joins here are just intersection and union, and this is an exercise that you had some time in first year, whatever, I don't know which lecture you do that in, but we know that intersections distribute over unions. So this is good. This is a nice thing. However, the lattice of non-crossing partitions of z with a point at infinity, in fact, the lattice of no crossing partitions very quickly. If you go beyond, very small set. If you have a 3-element set here, this is non-distributive. Okay, so how do we see that? And I know I had a couple of questions about how to intersect these non-crossing partitions, how to take the join and the meet, so maybe we can do an example now. Just in an example. So why is that not distributive, right? I can draw any non-crossing partition of this set by saying, okay, put a point at minus infinity here, and then connect numbers if they lie in the same block. What can we do here? Okay, maybe it's a bit of a small example, but you could look at the non-crossing partition little l. We have just one block of size 2, but we have all the rest are singleton. And then we got to look at m, which also has one block of size 2 with 0 and 1, and we're going to look at n, which has one block of 2 with minus 0 and 0. Minus 1 and 0. Minus 0. Okay. So something like that. So let's check if distributivity holds here. And spoiler alert, it will not. Because what is L join M? So what we're doing is we're intersecting all the blocks pairwise. So we're going to look at any block and we're going to intersect them. For the singleton, this is easy. You just get the singletons out, yeah? The only blocks we have to really look at is minus 1, 1 and 0, 1. And we see that these only intersect in 1, so it falls apart into singletons. So this is the finest partition, where every block is just a singleton, because you don't get anything bigger in any intersection of the blocks. This is the same as L intersected N. Well, not intersected, sorry, L meet N. So that means that if you have, if you take L meets M, join L meets N, that is still just all the singletons, because if you take the join of two non-crossing partitions, you just melt together all the blocks that touch or cross, but everything here is a singleton. So it's still the finest partition. On the other hand, if you look at M join N, now something a bit more interesting happens. If you look at M join N, it looks like this. So you have these two blocks in there, and you have to melt them together to a bit bigger block, so we still have a partition. So minus 1 and 1 also have to lie in the same block now. And that's the picture we have here of M join N. So if we take the meet with L, we still intersect all the blocks, and now we have a block here that contains these 3 elements. We can intersect it with the block here that contains these 2 elements, and we get a block of size 2. And you see here, this example worked very locally, just for 3 guys. So as long as you have 3 guys in there, you're already doomed. You're not going to be distributed. So that's the reason.
I mean, you just shown that this lattice with 3 elements is the sublattice.
Exactly. So you have this lattice of 3 elements as a sublattice, and it's not distributed. So you're going to find the diamond.
Shouldn't the non-crossing condition mean that L sort of must contain 0? Why is this intersection or the means of L?
No. So this would really just be no. So this just means minus 1 and 1 are in a block together, and everything else is a singleton. So 0 would be its own block.
then isn't that crossing with 0 and 1, or is the only both relation
Oh, so
just...
okay, what do I mean by crossing? Sorry. So you always need two elements. So you need this interlacing. You need a guy in your first block, then a guy in your second block, a guy in your first block again, and again a guy in your second block. So the crossing only works if you really can draw them as arcs somehow that cross. So that is no crossing, that is fine. If you don't see a crossing, very naively pictorially, you're not going to have a crossing. All right, good. Now, we have seen examples of non-crossing graphs. Maybe I can just, we can time now. So I use this example because I think it's cute. You start with a polynomial ring, you just put a grading on it, everything breaks. So that's the narrative, but there's much simpler examples of things that are non-distributive, lattices of the subcategories that are non-distributive. So you have this famous result by Ingles and Thomas. Which states that if you have an orientation of an ABE diagram, then if you look at the boundary derived category, finitely generated multi-KQ modules, this lattice of 6 subcategories is actually isomorphic to the non-crossing partitions of an ID diagram delta, non-crossing partitions of type delta. I'm not going to tell you what they are. If you want, I can point you towards the paper. It's a beautiful combinatorial description. Important for us, if this is a diagram of type A, then these are really just non-crossing partitions of, if it's AN, it's non-crossing partitions of 0 up to n. So this is basically an A infinity situation, which should not surprise us, since somewhere on here there's an A infinity. A double infinity. Okay. So I wanted to end with that because at the end of last term, David asked this excellent question: if there's a philosophical reason that if we come from finite dimensional algebras, we're not going to find distributive lattices. And I said like exceptional collections. And so maybe I want to circle back to that. Is that an obstruction to distributivity? Are exceptional collections? And you're going to quite easily find those in the finite dimensional algebra. So what is the statement here? The statement is that if you have a k-linear finite generated category, then it has an exceptional pair E1, E2. I'll tell you what that is in a moment, such that we don't have any maps from, so you have some maps from E1 to some shift of E2. So it's somehow a meaningful exception collection, which is not completely destroyed. Then the lattice of the subcategory cannot be distributed. Right, let me tell you what that means. It means that E1 each of these objects, EI, is exceptional. So we don't have any higher self-extensions. Only map we have from EI to itself is in degree 0. Okay. If J is 0 and 0 else. And we also don't have any maps at all going backwards. So you have that the maps from E2 to any suspension of E1 are 0. So that's an exceptional pair. Well, exceptional pairs in particular give you exceptional collections, give you examples of the subcategories. But what is the idea here? And I think I have just 2 minutes to very briefly tell you what the idea is. So you have your exceptional pair E1, E2, and there is a process of mutation of an exceptional pair, which you can formalize and say what that is. But you can mutate E2 along E1 to get a new exceptional pair, F to E1. So you can find such an F naturally somehow. They're constructed. And the point is, this F is now a new thing. It certainly cannot be E1, because otherwise you get maps of some degree backwards, of degree 0, so that's not allowed. But it can also not be E2 by this addition of the assumption that we know we have a map of some degree from E1 to E2. So F is a completely new thing. And now you see that you find a sublattice, because you're exceptional, your collection is exceptional, you're not going to have interaction between the 6 subcategories generated by E1 and E2, or E1, E2, and F. So you get a sublattice like that in there, so you get the diamond in there, and that's of course enough to break distributivity. So, I think I'm at the end of my talk, but that tells us that the finite dimensional algebra world is somewhere where we should expect non-distributive things to happen. And that's central for us, because for the rest of the lecture series, we're going to talk a little bit more about how can lattices of the subcategories look like, what kind of properties do they have. We're going to find that they can be of almost any shape. So if you want something, you probably can find something. Some things not, but many things you can find. And then we want to talk about the beautiful thing is that if you're in these classical, in these commutative ring situations, or many of you I think have been at this Oberwolfach masterclass school thing, you're talking about TT geometry. If you're in the TT world, you have stuff that's controlled by space. We don't have that on the dot in the finite dimensional algebra world, but we're going to show you how we can still approximate these things by a space, so we can still use these topological and geometrical tools. All right, so that's the end for today.
Are there any questions or comments?
When you do localization that is black hole that they hidden, is it possible to recover the lattice of fixed subcategories from the one of the localization and the shadow?
So the question is if you have a localization.
Yeah, for example, here when you do the localization, we know the lattice of fixed subcategories in the localization. We know what further is. It's possible to recover the one.
Oh, that's a really good question. Can you, like, if you know the lattice of fixed subcategories here, can you find the lattice down?
No, the way around. If you know it in the localization.
Can you know where to insert? Okay, that's the more interesting. That's the more interesting direction. Can you somehow know where to insert it back? No, I don't think so. That is my. I have to think about it, but I believe not, because the thing is you don't we're not very good at knowing the lattice of the subcategories. So I wouldn't see how immediately. And given that if you knew how, I think you could construct a bunch of examples. I would say the answer is no. Not easily. If you find a way, you're very good.
I mean, because in this case, you get the great idea of theorem.
Yeah. Oh no, I mean, like definitely here. So here, if you think about this here, like if you look at the lattice, like you lose a bunch of copies of Z in your lattice, right, that you have from here. And I feel like it will be very hard to recover that copy. I mean, there's nothing that tells you that you should recover. Why should you get all of Z, why not less? Yeah, David.
So the two counterexamples of this non-distributive lattices was controlled by these non-crossing partitions. And I wonder, I was asking like are there like some sort of theory that says these nice triangulated categories, their fixed subcategories are controlled by non-crossing partitions of some sort of set? Like it's controlled by lattice spaces. That makes any sense.
So you're asking, can I tell you which kind of categories, the lattice of subcategories, is controlled by non-crossing partitions?
Yes.
Oh, it's an interesting question. I can give you examples.
Yeah. Somehow
This is because if you're asking about like what kind of lattices of the subcategories are described in the finite dimensional algebra world, it's actually not that many. But whenever they are, non-crossing partitions show up. So there's this result by Curler. She classifies the subcategories for 10 hereditary guys. So this would fall in there, yeah. And she shows that basically the 6 subcategories you get from these pre-injective components, they're governed by non-crossing partitions of that type of the quiver. So the exceptional collections. I think this is a result. Okay, maybe I'm misciting, in which case I apologize. I think it's Igusa and Schiffler. They show that if you have a quiver, then the exceptional collections are classified by non-crossing partitions of type of that quiver.
In the definition of an exceptional collection, is there some generation assumption?
No.
Or so do you get that the?
I mean, if you want a no. This is just a small subset. The big the subcategory is going to be much bigger in general.
But you know that the mutation doesn't change the fixed subcategory, right? Okay, because you mutate based on triangle. Okay.
I didn't tell you how to mutate, but yes, it takes some approximation. Did the code.
So what's the relation to symmetric monodic structures on the triangulated category?
Well, you don't really have a tensor product here, right?
Yeah, of course. I mean, but like if you have an exceptional pair, does this also exclude the existence of a symmetric monodic structure?
Oh no, because like even there, like if you just know that radical thick tensor ideals are distributive, but you don't really, in general, you don't really know anything, except in nice examples, you don't really know anything about the whole lattice of thick subcategories.
In this case of the Kronecker, the derived category of the Kronecker is equivalent to the derived category of T1, and then there's.
Yeah, that's true.
You just don't see the tensor code naturally from this quiver.
If there are no more questions, then we should thank Sira again.